about the computer organization subject. In this subject, I'm going to discuss about the unit 3. And in the previous class, we have discussed some topics about this unit 2, that is register transfer language, register transfer, and bus and memory transfer, and arithmetic microoperations. So these are the different topics we have in the unit 2. And first, we have discussed about the register transfer language and register transfer. So what is mean by register transfer language? Register transfer language means this register transfer language means we are using the language. The register contains the operations and performing the operations and stored in them and stored data is to be stored in them. Okay, na? So this is called the register. Okay, register transfer. So in this register transfer, register set of register contains their functions and sequence of micro operations performed on a binary information and stored in the register. It is controlled by the sequence of micro operations. Next, coming to register transfer. What is mean by register transfer? So register transfer is nothing but we are going to denote or design the data in the form of capital letters, or sometimes we can use numerals. So whatever the functions we are writing in the register, that can be written in the design capital letters and numerals. So for example, MER, move, MO, we move, and whatever the things we are taking, that all written in the capital letters. Okay. And next coming to bus. These are the diagram of the registers, how we are representing. And in the previous class, we have discussed about this topic. I'm just recollecting the points. And now I'm going to discuss about the bus and memory transfer. So what is mean by bus and memory transfer? What we have learned about this, in this we having the register. We have has many register and paths must be provided to transfer information from one register to another. So in order to transfer information from one register to another, we are having the many registers and paths. So that is called the typical digital computer. A bus structure consists of a set of common lines. A bus structure that contains the common lines. మనకి బస్ స్ట్రక్చర్ లో కామన్ లైన్స్ అనేది ఉంటాయి. వన్ ఈచ్ బిట్ ఆఫ్ ద రిజిస్టర్. సో ప్రతి ఒక్క లైన్ కి ఒక బిట్ అనేది రిజిస్టర్ చేస్తాం. సో it contains the set of common lines and one for each bit of a register. So which binary information is transformed one at a time, and control signals determines which registers is selected by the bus during each particular register transfer. So this is called the bus structure. So we have the one way of constructing a common bus. So this is the diagram of the bus. So in previous class we have seen this diagram. So we have learned some points about this bus and memory transfer. So and in this bus structure, so these are the multiplexers. We having the 4 multiplexers and 4 registers. Okay, register A, B, C, and D, and we having the 4 multiplexers, that is contains the 4 into 1. Okay, so 4 into 1. So every we having the, these are the lines which are observing here in the diagram. So those lines are the those lines are the bus lines. Okay, na? So those lines are the bus lines. So in the bus structure, it contains some common lines. So these are the common lines for each one line. Each one line we contains. So each one line. So what we see saying that for every line we are giving one bit is registered. For every line, one bit is registered, and information is transferred for one at a time. So control signals will be used to determine which register is selected by the bus during each particular register transfer. So one way of constructing a common bus system is with multiplexers. A multiplexer select the source register whose binary information is placed on the bus. The construction of bus system for 4 registers is shown in the figure. So each register has 4 bits numbered 0 through 3. Okay. So if you see the diagram, you can understand very easily. So in the bus consists of 4 into 1 multiplexers, which each having 4 data inputs 0 through 3. So and 2 selection inputs S1 and S0. So if you see the diagram, you can understand very easily. So this is the 4 multiplexer, 4 into 1, 4 into 1, 4 into 1, 4 multiplexer we are having, and we are counting. That is, we are counting from 0 to 3. So 0, 3, multiplexer 0, multiplexer 1, multiplexer 2, multiplexer 3. So we are having the inputs, that is S0 and S1. So we are having 2 inputs. We have 2 selection inputs, S1 and S0. In order not to complicate the diagram with the 16 lines crossing each other. So here we are using the 16 lines that is crossing with each other, and we are using the labels shown in the connection output of the registers to the inputs of the multiplexers. So, for example, we having the output one of a register A is connected to the input 0 of multiplexer 1. So, this is the output one, out one of the register A. Output one of the register A is connected to the input 0 multiplexer 1, and because this input is labeled A1, and the diagram shows that the bits in the same significant position in each registers are connected to the data inputs one multiplexer to form one line of the bus. So this is the example of the bus, and this is the main diagram of the bus registers. So these are the registers, these are the number of multiplexers we are having. For every multiplexer, we are having the common lines. For in this each common line will be assigned a common 1 bit registered. Okay, so these are the registers, register A, B, C, D. These are the inputs. Okay, these are the 4 lines common bus, which is give the output. So these are the bus structure. Okay, so we having the two selection lines, that is S1 and S0 are connected to the selection inputs of all the 4 multiplexers. So 4 multiplexers ki manamu 2 inputs తీసుకున్నాము, S0 and S1 అనేది. Okay, so and the selection lines, how we are selecting the lines, we are choosing the 4 bits of one register and transfer them into the 4 lines common bus. When S1 S0 is equal to 00, the 0 data inputs of all 4 multiplexers are selected and applied to the output that form the bus. Okay, so this is the table having, if you take the bus input values 00, we will select the register A. If you select the input register input values, that is 01, we select the register B, and if you use 10, we will select the C. 11, if you having the 11 values, we will select the register D. So this is the table form of the bus. Okay, next coming to in general, we are having the some symbolic statements. In this, we are having some symbolic statements that can be transferred, may mention the bus or its presence may be implied in the statement. The bus is included in the statement. The register transfer is symbolized as bus. Use tries to C, R1 gives rise to, I mean, arrow is given to bus. So C value, whatever the information available in the C, that can be stored in the bus, and whatever the information are available in the bus, that is stored in the moves in the R1 register R1. So the control register C, the control register C is placed in the bus, and the content of the bus is loaded into the register R1 by activating its load control input. If the bus is known as existing in the system, it may be convenient just to show the direct transfer, that is R1 gives rise to C1. We can use the direct transmission, R1 gives rise to C. So whatever the information available in the C, that can be loaded in the register R1. So this is the content of the register C. So next coming to, now we are going to discuss about the three-state buses buffers. Three-state bus buffers. So a bus system can be constructed with 3 gates instead of multiplexers. So we are having the bus system that can be constructed with 3 gates instead of multiplexers. The three-state gate is a digital circuit that exhibits the 3 states. Two of the states are signals. Two of the states are signals equivalent to logic 1 and 0. Okay, na? So what is that saying? The bus system can be constructed with 3 state gates instead of multiplexers. A three-state gate is digital circuit that exhibits 3 states. Two of the states are signals equivalent to logic 1 and 0, and it is conventional gate. So the third state is the high impedance state. The high impedance state is like an open circuit, which means that the output is disconnected and does not have a logic significance. So that is called the third state. Next, three-state gates. Three-state gates. So it may perform any conventional logic such as AND or NAND. When the control input is equal to 1, the output is enabled, and the gate behaves like any conventional buffer with the output equals to the normal input. When the control input is 0, the output is disabled and the gate goes to the high impedance state. So regardless of the value in the normal input, this is the normal normal input. So what is it saying that? So we did the three. It is a three-state buses buffer. We having the three-state bus buffer. In this, we are constructing with the three-state gates instead of multiplexer. So this is the diagram. So instead of multiplexer, we are using the three-state gates instead of multiplexer. So multiplexer place of three-state gates అనేది use చేస్తున్నాము. So in the three-state gates is digital circuit exhibit the three states. Two of the states are signals and equivalent to logic 1 and 0. Logic 1 and 0 and conventional gate. The third state, the high impedance state. The high impedance state behaves like an open circuit, which means that the output is disconnected and does not have a logic significance. The three-state gates may perform any conventional logic such as AND or NAND. When control unit is equal to 1, the output is enabled and the gate behaves like any conventional buffer with the output equals to normal input. When the control input is the output is disabled and the gate goes to high impedance state regardless to the value in the normal input. So this is three-state bus buffer. So in this is the diagram of the three state. This is the diagram of the state. We are going in this. We are having the graphic symbols of state buffer. Gate is shown in the here. So in this we are having the it is distinguished from normal buffer, and by having both the normal input and the control unit, both input and control unit determines the output state. When the control unit is equal to 1, the output is enabled and the gate behaves like any conventional buffer with the output equal to normal. Input is equal to 0, the output is disabled and the gate goes to a high impedance state. The high impedance state of the three-state gate provides a special features not available in the three-state gate provides available in the other gates. The three-state gates outputs can be connected with wires to form a common bus line without any loading effects. So what is the main distinguish we are having? Normal buffer having the both. Normal buffer lo manaki em both input and control input. Normal input and control input rendu untayi. So control input yokka use entante output state. The output control input determines the output state. Control input ante enti? It will be determines the look like a output state. When the control input is equal to 1, control input అనేది equal to 1 అయితే the output is enabled and the gate behaves like any conventional buffer. The output equals to normal input. When the control unit input is equal to 0, the output is disabled and the gate goes to the high impedance state. And the high impedance state of the three-state gate provides a special features not available in the other gates. The three-state gates outputs can be connected with the wires to form a common bus line without any loading and effects. So this is the four A, B, C, D. These are the registers and bus lines for these are the bus lines for bit 0, and these are the inputs. So this is 0, S0 and S1. This is the decoder, and we having selecting the we have cell S1 and S2 input. If it is enabled, if we are going to select this, okay. So this is the normal input A, B, A, and control input C. Okay, and output we are having the Y is equal to A. If C is equal to 1, high impedance. If C is equal to 0, it is not a impedance. So okay, in this we are having the construction of the bus system. So this in this the construction of the bus system with a three-state buffer as shown in the figure. In this figure, we having the three-state is S0, S1, and the outputs of the four buffers. These are the outputs of the four buffers are connected to form a single bus line. And the control inputs of the buffer determine which of the four normal inputs will communicate with the bus. So no more than one buffer may be active state at any time, remaining or maintained in a high high impedance state. And one way to ensure that no more than one control input is active at any given time is to decoder, as shown in figure. When the enable input of the decoder is 0, all four inputs are 0, and the bus line is in a high impedance state. When an enabled input is 1 of the three state buffer will be active, and depending on the binary values, it selects the inputs of the decoder. To construct a common bus for four registers of n bits, each using three state buffers, we need n circuits with the four buffers, and each common output will be produced. So this is called the bus structure. Okay, next coming memory transfer. So bus transfer, this is a memory transfer. So in this memory transfer of information, a memory you owed to the outside environment is called read operation. So the transfer of new information to be stored into the memory is called a write operation. So in this memory word will be symbolized by the letter M. The particular memory word among the many available is selected by the memory address during the transfer. So in this we are having the control of the memory unit that receives the address from the registers called the address register, symbolized by AR. So AR means what? Address register. And the data are transformed to another register called the data register, symbolized by DR. The read operations can be stated as follows. That is a read DR, and the data registered, and that is M of AR. So causes the transfer of information into DR from the memory word M selected by the address in AR. So this is the working of memory transfer. So next coming to, this is the table of the arithmetic in micro operations. Okay. So what is mean by arithmetic micro operations? So in this arithmetic micro operations, we having the table. So this is the main table we are having. So symbolic the representation of the description, designation, and this is the description of this symbolic representation. And R3 gives rise to R1 plus R2. The content of R1 plus R2 transfer to R3. So the content of R1 minus R2 transfer to R3. The content complements the content R2 one's complement. So complements, if you use the complements, so we can be converted into one's complement. If you use one's complement plus whatever the value occurred, that for that value we are adding the 1. And this is also same, R1 plus the 2's complement of R2 and subtraction. So R is given gives rise to R1 plus 1, increment of the content R1 by 1, and decrement of the content of R1 by 1. This is the tabular column. These are the tabular columns which we have here. Okay. And next coming to uh, this is the table column of the arithmetic micro operations. So in this we having, in these micro operations most often used in digital computers, classified into 4 categories. So register transfer micro operations transfer binary information. Register transfer micro operation transfers binary information from one register to another. Arithmetic micro operations perform arithmetic operations on numeric data stored in registers, and logic micro operations perform bit manipulation operations on numeric data stored in registers. So shift micro operations perform shift operations on data stored in register. The basic arithmetic micro operations are the additions, subtraction, increment, decrement, and shift. The basic arithmetic operations what ma? Addition, subtraction, increment, decrement, and shift. So in the arithmetic micro operations defined by the statement R3 gives rise to R1 plus R2, it specifies that an addition micro operations, it states that the content of register R1 are added to the content of added to the content. So whatever the values information available in the register R1 that are added to content of register R2, and the sums transferred to register R3. The other micro operations are listed below. So So this is the main explanation of this example. So next binary. Next this is the symbol. I having got I already told the symbolic representation. So that is R3 register to R1 plus R2, R3 register R1 minus 4. So if we have the plus, we can use the increment operation. Use the minus, we use the minus operations. So this is called the memory transfer. Next, binary adder. What is mean by binary adder? To implement an addition micro adder, in order to implement an addition micro operations with a network, we have with a hardware, we need two registers to hold the data and digital components that perform the arithmetic additions. The digital circuit that forms the arithmetic sum of two bits and the previous carry is called a full adder. Full adder, the digital circuit that generates the arithmetic sum of two binary numbers of any length is called binary adder. So the binary adder is constructed with a full address cascade to each other. So in this, we are having the interconnections of four full adders, FA, to provide the 4-bit binary adder. So in this, binary adder is constructed with full address circuit connected to cascade with output carry from the full adder connected to the input carry of the next full adder. So next input carry out to the binary adder, input carry to the binary adder C0, and the output carry is C4. The S is the output of the full adder generates the required sum bits. So next, this is the 4 binary adder. I having this is the FA. This is Wi-Fi means what? What is mean by FA? Full adder. Okay, FA is a full adder, and we having the C1, C0, C1, C2, C3, and C4. And these are the input S1, S2, S3, S0, and A3, B3, A3, B2, A2, B2. These are the different outputs of the register binary adder. So this is the diagram. Next, binary adder subtraction. So the subtraction of the binary adder binary operations can be combined into common circuit by including an exclusive or gateway with each full adder. A 4-bit adder subtract can be shown in the figure. So the mode input M controls the other operation. With M is equal to 0, the circuit is an adder, and when M is equal to 1, the circuit becomes subtractor. This is the diagram of this adder subtraction. So each XOR in this if you see this diagram, I have explanation. We can I'm going to explain this diagram. The XOR gate receives input M. Each XOR gate receives input M, and one of the inputs of B. When M is equal to 0, we have B plus 0 is equal to B. The full adder receives the apple of B. The input carry is 0, then the circuit performs a plus B. So when M is equal to 1, we have B plus 1, that we can return in the B's complement. C is equal to 1, we can return B's B inputs are all the complement, and one is added to the input carry. The circuit perform operations A plus 2's complement uh, B for unsigned numbers. This gives A minus B if A greater than B, or the 2's complement of B minus A if A greater than less than B. For signals numerals numbers, the result is A minus B. So this is called the binary subtraction. Next, binary increment. So what is meant by binary increment? In this binary increment, micro operations added one to the numeral in the registers. So the diagram of this, I have the diagram, that is 0, 110 plus 1 and is equal to 0, 0, 1, 1, 1. So in this diagram, we having the 4-bit combination. Behind this, we having the 4-bit combination circuit incremented shown in the figure. One of the 5 inputs to the least significant handle orders HA is loaded, is connected to the logic 1. and other input is converted into USB of the number to be incremented. So the output carry of HA is connected to one of the inputs of the next uh, higher order. The circuit receives the 4 bits from A0, that's through A3, adds one to it, and generates the increment output. If yes, S0 through S3, the output carry SC4 will be 1 only after incrementing binary 1 this or causes in outputs. So S3 to go S0, the circuit diagram can be extended to an n-bit binary increments by extending the diagram in diagram in include a n half adder, n half adder. So next coming to the, this is the explanation of this 4-bit binary, and this is a tabular column we have explained in the last class, and these are the brief explanation of this. This diagram of the subtraction circuit. And next coming to the, this is the conditions when S is 1, S is 0 is equal to 0, 0. The value of B applied to Y inputs of the adder. If C in is equal to 0, the output D is equal to A plus B. If C in is equal to 1, the output D is equal to A plus B. And if C in is equal to 0, the output D is equal to A plus B. If C M is equal to M in is equal to 1, the output D A plus B is plus 1. Both cases perform the add micro operation with or without adding the input carry. So this is the condition of the first one. So next condition is S1 and S0. If you use the condition that is 0, 1, so the complement of B is applied to the Y and input of adder. If C in is equal to 1, then D is equal to A plus B plus 1. So this is the S1, S0 incrementation. When C in is equal to 0, then D is equal to A plus B. The equivalent of the subtraction with a barrow, that is A minus B minus 1. When S1 is equal to 0, then the input of from B are neglected, and instead of all zeros are inserted into the Y inputs. So the output becomes D is equal to A plus 0 plus C C in, it is gives to A is equal to D is equal to A, when C in is equal to 0 and D is equal to A plus 1. When C in is equal to 1, if the case we have direct transfer from input A to output D. So this is the in the second case. If you talk about the second case, the value of A is incremented by 1. When S1 S0 is equal to 1 1, all the ones are inserted into the Y input of the adder and produces the decrement operations. D is equal to A minus 1 when in is equal C in is equal to 0. So this is because a number with all ones equal to 2's complement of ones and 2's complement of binary 0001 is 111. Adding a number A to the 2's complement of produces F is equal to A plus 2's complement of A of 1 is equal to A minus 1. When C in is equal to 1, then D is equal to A minus 1 plus 1 is equal to A, which causes the direct transfer from input A to output D. So these are the two cases we are having in the binary. So in the next class, we will discuss about the logic micro operations. Okay, we don't have a lot of time, so we'll discuss in the next class. But thank you for listening this class, ma. So if you have